Hello, welcome to another one of these videos. Here we will continue exploring op-amps. By using feedback loops and taking advantage of the properties of op-amp, you can create a variety of useful circuits or sub-circuits. So let's talk about a few of those. Let's start with a very easy setup, a voltage follower. The feedback loop stabilizes the open loop gain so that the output voltage follows the input voltage. A voltage follower, just as the name implies, will have the output mimic the input, so your Vout equals Vin. Yep, it sounds very useful, behaving just like a wire. Well, actually, there is some merit in doing this. Whenever we put together a multi-stage circuit, we have to keep in mind the impedances, or the ratio of impedances, from one part to another. This can have a drastic effect on your voltage signal, making it weaker. You can think of it as having essentially a voltage divider between the two parts of the circuit. The impedance between the two circuits shouldn't be too different, or should not be opposite. For example, the first part of your circuit having a high output impedance, and then having the next part requiring a low input impedance. Here you have a mismatch. Your circuit requiring a small impedance next, but already having a high impedance. A voltage follower aims to correct that. Just add this circuit in between, and you are back in business. But be careful with stability issues. Let's move along to the next circuit. Moving on to a similar easy circuit, we have the comparator. Now in this case, we don't use a feedback loop, so the open loop gain of the op-amp will just make the input as large as our source voltage allows us to. In this case, we can use the fact to emphasize the difference between the two inputs. We can use the reference voltage to compare or test our input voltage. This reference voltage is created by you to gather some useful information. You will use it to know when Vin is bigger or smaller than that reference voltage. This can be used to perhaps get some useful information, say battery level getting too low. However, this comparison can have far more reaching applications, because this comparison can be thought of as a 0 or 1. This should sound familiar if you know a bit about digital logic. This can be used in a part of a digital converter, taking us into the realm of digital logic. Let's move on to another useful circuit. I have discussed filters in previous video, but the op-amps can create a more variety of filters. There's a bandpass filter, which allows a range or a band of frequencies, say only 200 to 3000 Hz, to pass through while rejecting everything else. All you need to do is put together a high pass and low pass filter as shown here. The band reject filter is just the opposite of the band pass filter. It rejects a band of frequencies while letting everything else go through. This is created by adding together a low pass filter and a high pass filter as shown here. And then there is the notch filter. This tries to reject just a single frequency. It is most commonly used to reduce the noise from a nearby electronics, which operate at around 50 or 60 Hz, depending on where you live. There are many more filters that can be created, like second order filters or higher order filters. Let's go on to the next circuit. The summer op-amp circuit. When you have multiple input voltages, an easy operation that you may want to do is add them together. The summer op-amp adds weighted inputs. Their weights, or how much you add of each input, is determined by their respective resistors. so you can make them as pronounced as you would like. The op-amp serves as a gain, allowing these inputs to add up without loss in the signal strength. Addition is a fundamental and the most basic mathematical operation, which can be useful for a variety of applications. In fact, I have already used it for the band reject filter. This makes it a very essential and powerful basic circuit. The differentiator is an op-amp that outputs the derivative of the input signal. It uses the inherent physical properties of a capacitor to create a differentiator. This has a variety of uses. It's used for analysis of the circuit. As you learn from derivatives, it can show you the rates of change or where your circuit is changing. Also, it can do a relatively simple peak detection, finding your max or min, like you learned in calculus. It can also show you where you have high frequencies and noise, since this is very sensitive to changes. Besides this, it can be used in analog circuits as a control mechanism, where this rate of change can be used as a trigger to change the behavior of your circuit. This is useful in a variety of applications, where you can think of it as a basic sub-circuit. Of course, using the op-amp, you do simulations of what frequencies you can use for your input. Let's take a chance to look at the circuit analysis of the circuit to show exactly how this is acting like a derivative. We can start by using node voltage. Just like before, we're going to be interested in the currents going through this op-amp. So we have the negative voltage of the input divided by the impedance of the capacitor plus the negative voltage of the output divided by resistance should equal 0. However, for the current going through the capacitor, you could also think of it as the capacitance times the derivative of the input voltage. So we can rewrite this as negative C dV over dt plus negative V out over R is equal to 0. Solving for V out, we get V out is equal to negative RC times the derivative of your input. And there you go. This is how you get the derivative of your input for your output voltage. Just like the previous circuit, we have the integrator circuit, which follows the major concept you learned in calculus class. This takes the integral of your input signal. It looks similar to the differentiator circuit, where the only difference is that the capacitor and the resistor have swapped places. We can use the circuit to find the changes in the input over time. It can also be used as a control mechanism. Having the ability to sum up the behavior of a signal or a portion of the signal is powerful. For example, together with the previous circuit, the differentiator, it can build a PID control circuit or a proportional integral derivative controller. With this, the integrator is used to sum up the error and help correct the output to a desired amount. And let's see how the capacitor is used to get an integral in this circuit. Just like before, we'll start off with node voltage. We have negative V in over R plus negative V out over the impedance of the capacitor is equal to 0. We can again rewrite the current going through the capacitor as capacitance times the derivative of V out. So we can rewrite this as negative V in over R minus C times the derivative of V out is equal to 0. Solving for V out, we get the derivative of V out is equal to negative V in over RC. Taking the integral of both sides, and we get V out is equal to negative 1 over RC times the integral of V in over time. And there you go. We have, again, found V out with respect to V in. There are many types of amplifiers that make use of the op-amps. A great example of this happens to be the instrumentation amplifier. The instrumentation amplifier, or in-amp, is a common mode rejection amplifier, which just means that this is a type of amplifier that amplifies the differences of the inputs. This is a great amplifier for small signals, much like those you will see within biological systems. The analysis of this amplifier is much more involved, so I will save the analysis of the circuit for another video. Go ahead and try it out yourself. A useful hint is to use superposition as well as node voltage that we have previously covered. And those are all the different types of op-amp circuits that will be covered here. There are still many more. Thank you for watching.